Hi, welcome to Coffee Compiler Club. Anything to do with coffee and compilers and language runtimes. And we're all old hat. Y'all know you're being videoed. The video shows up on YouTube within, a couple hours. That's it. That's a good enough start. I think last week we talked about AA for a long time. I'll throw out the short version of what I've been going on. If you want to go there again, we can. I gave up on approx. I've been working on it for more than a month. I gave up on it being either not monotonic or sucking. And I had to do a bunch of algorithm changes to take care of places where the presence of approx gave me information that I no longer had, and either got it from somewhere else or I had to rejigger how it recomputed things so that oh no. Well, that was the microphone falling because I'm screwing around because there it goes. Yeah, it's like it won't stay now. Man, oh man. So there you go. I'm trying to get it not in my camera like that. Why is that not the problem? Okay, fine. There's a comedy of errors. Anyhow, went well enough. Mostly I boiled it down to now this morning I have 4 remaining tests out of a couple hundred that are not reporting correct, of which 2 are progress bugs as opposed to monotonicity bugs, that's a big step up. Progress bugs just mean I missed a place for somebody to go back on the work list after some other change happened because I didn't have the information I wanted, so I went looking for it too far remote, and because I went looking for it far remote, somebody far remote made a dependency when they improved on somebody else. So yeah, progress. That's what it amounted to. Some things look a lot better in terms of what the golden results are coming out are actually somewhat improved. So I don't know. A couple more days and I'll probably have it nailed, and then life will go on. And after that, I had some real life interventions going on that were unrelated to medical, just household things. And I spent a lot of time doing bathroom upgrades or downgrades or something.
You should get Gregor Hope to visit.
Who?
Do you know Gregor Hope?
No, is he in the Bay Area? Does he do bathrooms?
He's currently moving around the world redoing condos one at a time. Right now he's in Thailand having a horrible time.
We have flipped 2 homes and kind of enjoyed the work and made good money at it. So my old home, her old home. So we're debating moving again and getting an us home instead of a my home. And that means fixing up some stuff in this place. Not too bad. And the prior guy who worked on the house and sold it, flipped it, he was like a handyman, except a worse one than me by a fair amount. He blew a bunch of things. Like he installed the kitchen exhaust fan, has a knockout panel it ships with, supposed to knock it out to let the airflow through. Well, he didn't bother to knock it out. He just installed it. So for 6 months, I couldn't figure out why the kitchen exhaust fan sucked. So I basically dismounted, the fan over the kitchen and took it apart and was like, what's blocking the chimney up? No, the block was right in the damn exhaust, and it was
I think what you said was a little incorrect. You said it sucked, and the problem was it probably didn't.
Yeah, it didn't suck. Yeah, exactly. Yep, that's it. Hey, Bill, I gotta figure out your.
Hey, he's got a big kitchen fan behind him.
There you go. Oh, yours works. Yours suck.
Sucks and blows.
Yeah. Why do I not see your name on here, Bill? You have a funny email, the mail mapping. Oh, that's because I moved you. Here, I found you now. Never mind.
Okay.
And here's Dan. All right, something else.
I'm working on rewriting a hash map.
Excellent. What's wrong with your hash map?
Nothing's wrong with it. Just trying to make it a little more efficient and a little more.
I went down in the land of my stupid types, I build these cyclic structures that I also return, so they're hashed. So if they're cyclic and you build them and you compute a hash with structural recursion, you infinitely cycle building your hash.
Yep.
So you have to not build your hash with structural recursion, but you want the hash to be pinned on the structure because that's what's unique about the thing.
Yep.
So I did all kind of caching games and had all kind of other bugs, but then I discovered I really can't make a closed cycle until I know that I'm done, and I can't hash it yet. So some points in the cycle have a really bad hash because they can't depend on their children, which they can't cycle through. So then I went down the path of how to make a better hash function with a tiny amount of information. I don't have a lot of information here. What's a good hash? And I found this thing. I threw it out in the link once
Yeah,
before.
you posted it before the
Verbal B or something. It's like there's some good theory about how to do hashing, and that's just hashing itself. Yeah, here, birtlebirdle.net. I'll throw it in the link in the chat because it was a fun little thing, and it led me down this path of, oh, not only do you want to get all the bits that you have, but you want to force them in the hash to spread about and depend on each other every spread. Well, this improved my hash function so much. It gave me like an order of magnitude speed up. I hadn't realized I had such bad hashing going on.
Yeah.
So then I put a profiling tool in my hash table that will tell me how many things are in there with what kind of reprobe count per each thing, and give me histogram of the reprobes. And a little screwing around got me a decent hash function now, but it didn't start out decent, and it was entirely silent. And I had thousands of things hitting the same bucket, and you're linking along a linear scan the bad way.
Is your stuff built in Java?
Oh yeah,
So
yeah.
So you're using Java's HashMap, which I think uses power of two.
No, Java's Java's HashMap does not use power of two. It uses primes. I use non-blocking HashMap frequently, which does use power of two. HashMap is prime numbers, baby.
No. Well, I've got so many bad memories that I can't remember.
Okay, fine. There was definitely a time, and I think it's still true today, that 101 was the initial size of the table, and was far too big as a default size.
But it always doubles, right?
And no, they did something to make it prime, or
I swear when they resize, it doubles.
Maybe it does. If you keep it odd after doubling, you're still not divisible by 2.
All right, so I'm in the code now. I'll take a look.
Go stare at what it actually does.
Much more complicated since Josh wrote it. So used to be like 100 lines of code. Now it's like 40,000.
Yeah.
Actually, that tree thing they added is pretty good.
Oh, I forgot. Oh God.
The list entry, the link.
I hate it, except it saves you from like broken hashes.
But it's also necessary because with the doubling in size, they end up pouring giant piles into certain buckets. I mean, that's the problem with not always using prime modulos. So what we do is we have a list of primes, and when we resize, we grab one of those.
Oh, that's interesting.
Yeah. I mean,
no, I've always been a fan of the doubling in size and cache hitting on reprobes, making reprobes relatively cheap. And then a better hash function. If your hash function sucks, your hash function sucks. And that's just that's a different issue. So old school, don't do a mod, which doesn't really count much anymore.
Yeah, so new cap equals old cap shift left 1. I'm going to say that doubles it.
Because I'm talking to realtors, I'll listen. But
so yeah, line 685 from JDK 17 anyway. New cap equals old cap shift left 1. So they double it.
Yeah, okay. And in fact, it was for my car's extended warranty.
So yeah, I mean, so you have to use prime modulos. I mean, but the problem with prime modulos is when you resize, instead of, so when you double in size, you take the hash map and you just do that basically. Well, actually you do that, right? Yeah. So each bucket moves generally half of its content, but it moves it all to one bucket. Yeah. So it gives you some optimizations when you double in size, right? Yeah. But if you change the modulo, everything goes like
Yeah, right. Yeah, yeah,
Because
yeah.
I'm sorry,
I don't.
it's a prime modulo.
Right, right. I don't do any of those optimizations on the resize, and it's never been an issue. The resize happens a few times and it's done. It quits doing it.
Yep.
And I don't care anymore. And in fact, for non-blocking hash map, the resize is incremental. So the cost to resize is smeared out in time, and not one poor dude pays it all at once.
Yeah, the other thing in Java, what we found was doing an open hashing implementation instead of a linked overflow is usually dramatically faster and dramatically smaller. Because what happens with the linked overflow is that unless you're allocating everything in the same sweep, right? So add all or whatever,
Yeah.
put all
Yeah.
in. You're basically, your allocations are random in memory, so you never get a cache hit with HashMap.
Yes.
If you do open hashing, some form of open hashing, then the map, both the keys and values can all be stored in the same object array. Right?
Yes.
So you have locality.
Yeah. Exactly what non-blocking hash map does. They're all in the same object array. Keys and values are side by side in pairs walking through the power of two, for me, sized array.
Okay.
And the reprobe is I used to do by ones. I think I now do by some other number than ones. Because it does help with people who are bad hashing. And then it turns out that my better answer was to just fix your hash function. So I probably should go back to reprobes by one and demand
there's nothing a hashing implementation can do if you mess up the
hash function. Yeah.
Yeah.
Right. Well, so what
it's a self-denial of service, basically.
Right. What I found from Doug Lee was that there was a lot of people who did screw it up, and that a tiny amount of adding a bit scrambler onto the user's hash function can sometimes rescue you. It doesn't rescue all the time. Certain folks are just going to suck anyhow. I think a better answer, actually, now that you've said all this, is that a default normal hash implementation should include a function which gives you that histogram of reprobes and a goodness factor that says something like, you can do a Boolean check that says that you suck, and then go ask for the histogram and diagnose bad hash functions.
Right.
Like diagnosing a bad hash function, it's like suck. For me, it required me to recognize it in the first place, then build a bunch of profiling tools that ultimately ended up with this thing I can do now that will give me the histogram.
If I remember correctly, the other problem that Java has is it has as a constructor parameter, if I remember, it takes a threshold percentage or something.
Yeah, load factor. Yeah, right.
Factor, which is idiotic. Why would you ever?
Exactly.
Like, first of all, the array itself is the cheapest part, right? So if your array is twice too big, who the fuck cares? Like, perfect, right? If it's, but you want it to be about 17% too big or whatever. There's some sweet spot where basically you never have more than one item in a bucket.
Yeah.
And that gives you actual one access time, right? If the hash code's any good, and if the module is not power of two, right?
Right.
And but letting someone set that percentage, like, total, like,
So I had the theory, and I have no idea if this is true, that the guess was somebody would want a hash table that is most of the maximum size allowable, and they want it to not grow anymore, but it be very, very large. And so the percentage had to be even bigger so that they could fill it up to the max. Is my guess. I don't know.
Yeah, I mean, it would be reasonable to give it an initial capacity, for example, to say plan to hold this many items.
Yeah, I guess I went back and forth on that on the non-blocking hash map as well, and I put it in because I had matched the JDK, so it's a drop-in replacement for concurrent hash map, and then they're like, whoever uses it and does it actually buy you anything? Because the first thing that happens for me is that it's a hot table, or you didn't care. Oh, it's a hot table. Well, then it grew really quick in the beginning, and then it's done growing, and it's all over. And if it wasn't a hot table, I didn't fucking care when you grew or how much you grew.
And then there's a couple other things too. So like, people assume it's 01 because it's a hash map, right? So even with a great hash function though, if your keys are 10 kilobyte strings.
Oh, well, you have to do a key compare.
Right. No, you have to hash it first.
and you have to hash it.
Okay. So
You have those strings, you have to hash them. That's correct.
Right. So it's 01, but in that case, a linked list would probably be faster. Like up to a certain size. Because
Well, no, because you have to still do a key compare, which means that every time you ask to probe the table, unless you get a direct hit pointer to pointer, you stop and you do. It was the whole point of hash tables.
But key compares immediately fail if there's a size difference, and they fail out on the first. They fail out on the first.
No, but I'm saying on a hit that's not a pointer quality hit,
right?
You walk that 10K string.
No, only if the first 9.9K is identical.
So I'm saying you walk the first. You walk the entire key of 10K to acknowledge a hit.
Yes, that's correct.
Right, and that right there is a minimum lower overhead on how long it takes to probe a hash table.
Yeah,
is to get a correct key compare. Now, if you're getting equality hits, that's free. But if you have to do a structural, I mean, and the point of the hash table is you're looking for structural hits.
Yeah, and the irony too is that if you actually look at the load, so by way of background, I have a lot of maps in my. I used to sell one. I'll put it that way. So I've written map implementations hundreds of times.
Yeah, I have plenty of maps as well.
And what ends up happening, if you look at the actual load in actual applications, you will almost always see the same key come in at least 2 times in a row. So for example, applications will say, if it contains X, then get X, then whatever X, like you'll see the same key show up repeatedly. And that's another one of the optimizations that's not there in the Java library.
Right. You mentioned that. I beat my head out of that, but I mean, you sound right to me that I ought to put it in all my tables. I don't use it in a concurrent setting because it's a concurrency bug.
I was just going to ask about, because I thought it was you, Cliff, mentioned it before about storing the most recent key.
Cameron did the optimization before. I remember that.
I was wondering about if that's synchronized or how that's because
if it's a concurrent data structure, you CAS it. Yeah.
Yes.
Okay.
So right. So in concurrency setting, anytime you read memory, and then you act on and then you do something else, and then you act on the memory that you read. I'm sorry. Then you read it again and act on it. Right. Okay. The second read can be different from the first read. And if you don't test it again, you're wrong. So the correct way to write any concurrent algorithm is to figure out what you need to read to make a decision, read it all, validate the data as a whole, and then act on the decision, but never read it again. Because if you ever read it again, you'll get a different answer. And now you have to recompute your decision-making process on the different answer. So, and then the action is that you then do one CAS to update something. And if the CAS succeeds, life is good and you got it. And if it failed, you have to go reread everything and revalidate everything.
Yeah, what I was thinking, I was imagining I look up a key, I get a value.
Yeah.
Well, actually, if it's just contains, I didn't even get the value. But if I had the key and the value, and then I want to store both those together in one little spot to remember it. Next time something comes in, I can check it. Is that the one that they're looking for? I can just use that value. That's what I was imagining.
Okay, so
it has to be, synchronized or
yes.
Something.
So if you're looking at a concurrent hash table and somebody sets the key with the value, and then you want to optimize, so you store the key and the value off to the side, somebody else comes and changes the value, and they probe the original table, and you're busy clearing your cache, and another third party comes in and probes the table, and they hit in the cache. You have a race going on between the 2 writes it takes to clear the value or set it to a different thing, and the guy who's reading it versus the probing it.
That would be a pretty bad design, though.
I'm just saying you could do it.
Okay.
And in fact, there's an easier one I would think you do is you'd have the index into the key into the table as an unrelated thing. Hey, I got this key. I can see that it has this index. I'll go into the table. I still see the key, and now I can do
there you go.
Things.
Well, for example, though, you could do as easily as just caching a tuple of the key and its hash code, right?
Yeah.
And so, and whether or not it exists or not. So if it comes in the second time, you already know whether it exists. You already know its hash code, so you don't have to recompute.
Well, if you probe the tuple before you probe the table, you are racing as a writer, you're racing against clearing the tuple in the table.
Obviously, with concurrent data structures, it gets more complicated.
Okay, fine.
Yeah.
Yeah, I don't use tuples for my key value pairs. They're just adjacent elements in an array.
The reason I said tuple was less about the data type and more about the idea that you could cas it in a single operation.
Oh.
So that's the only reason I use the words.
I don't think Java lets you cas double, or like x86 these days let you do 16 bytes, but I don't think Java lets you do it.
Java will let you cas along. I don't.
Yeah, that'll be.
And I think as part of John Rose's work on the was it Valhalla Panama something or other, they'll support casing larger.
Okay. Yeah, you could.
The requirements for the record stuff, but I don't fully understand it. So.
Well, if you want to do an atomic update of whatever size, x86 will now do 16 if they're cache line aligned, and been doing that for a while. But they won't do misaligned, and most processors won't do beyond 8.
Right. Yeah, I think 8
So
came out around 2000.
Double pointer on an x86 alone, but if you're on an ARM chip, you probably can't do double 8-byte pointers as a single atomic cas.
Yeah, I like the index one, because the other one, basically, the other one assumes something's not going to mutate too if you cache the hash code.
Well, right.
Oh, right. If the hash code changes, you're screwed.
Well, they're screwed, but yeah.
No, if the hash code changes,
you know what? If the hash code changes, that's true. The thing doesn't promise to give it back right now. You can miss it, so that's fine.
Right. So if you use a key and then its hash code changes, you put it in and you try to get it out.
It's already
You're already dead. Yeah, you're already dead. Yeah. Non-blocking HashMap doesn't. It relies on keys having immutable hashes as well, even when they're removed from the table.
Right.
When I resize a table, I'll toss the dead ones out. But if their hash changes and I resize, I can tell they're dead on a resize. No, it'd be broken if you were to put a key in the table, take it out of the table, change its hash, and put it in the table again. Right. That'll break me.
So brain fart.
All right.
What you were saying earlier about your circular.
The hash function sucking. Yes. So the circular types. Yes.
So we do the same thing in terms of basically interning the constants, like all the references to the various parts of the IR structure. And we have many of the, we actually had 2 different issues in that area. One is the natural circular references, and it's rare, but rare in terms of the design, not in terms of the frequency. So there's 1 or 2 things that can theoretically have a circular reference. And then, but the other one is that early in the compile stage, you simply have less information, right? So you have a name, but it doesn't have a meaning. And usually the hash code, once you get to a certain point, the hash code actually means something. It's based on what something is, not just what it's named, right? So you have something called Bob, but you don't know his last name, right? You don't know, is it a class? Is it a type? Is it a variable? Is it a property? It's something, right? But it's at this point, it's indeterminate, right? But you have to keep information related to it. So, you're storing it in a hash data structure. So it has to have a hash code.
And the hash code has to depend on what you have when you first meet to it, arrive at it.
Right. And later on, it gets more information, which gives it a different hash code. So now what do you do?
Okay.
So
I have a different solution here, but go ahead.
Well, the way I solved this the same way I did for the Java compiler I wrote, which was the constant, basically this representation has basically 2 forms. It's a kind of an unknown state where where it keeps that hash code forever, and then it has later on we create a different constant for the known state. And we link the unknown to the known, so that anyone who holds the unknown, anytime they dereference it, they automatically swap it out for the known state, so that by the time the compile cycle by the time the crank goes around 1 cycle, once it's been resolved, no one has a reference to the old indeterminate one. And then the assertion to make sure you didn't miss any of them, you basically make the unresolved one vomit anytime, panic anytime it has to do something that's real. So like write yourself to disk, boom, right? It's like you can't ask me to do these things because I'm not real, right?
Right. Yeah, having you thought through it while you were talking, I think I ended up doing roughly the same thing for user-written cyclic types. So I don't have any names typically when I'm doing inferencing. So if you make a cyclic type by doing a cyclic piece of code or recursive piece of code, then the types that come out of that they get cyclic from the get-go, and they don't have any staging like that. If you wrote a user-defined name for a type and then used it inside of the type, then I get a cycle because I put down semantic IR nodes representing the constructor that will yet be built for this named type. And the type that's inside of there is a sham, as you say. It's the half completed type. And then after I close the loop on the name for the constructor, I can now do it just like I do for recursive things. I can do a from whole cloth for the round the cycle type. But I don't typically have names for any of these things. So the hash is all about the structure of the type and not about any names involved.
How do you compute the hash when it's got a cycle in it, Bill? You kind of said you read a paper or something, but I mean, what do you do when you have a cycle? Or do you write?
Well, okay, so the paper was just if you had some bits that you were going to turn into a hash, what can you do to do a better job of turning them into a hash? It's an easy, short read, and also there's some code that I just cut and paste that does an amazing job. It's a small amount of fiddle. Okay, so just take the code. It's like fucking amazing. The actual how to do a cycle thing is I have to cut the cycle at some point where I can cut it with the maximum amount of information I can have without actually looping because I don't have the cycle yet. And for me, that happens to be a struct definition, which has fields. And so my cycles are going to be a pointer to a struct with a field that has a pointer to a struct. Okay, so the struct can know that he's got fields with names. And that's the maximum amount of information he gets. The fields have names, they have mutability constraints, they have an ordering within the struct. There is a name struct concept that's like subclassing that if I have one of those, that'll help, but I don't typically. So that's the amount of information I have, and that's my hash. Then later when I close the loop on the guy, that hash function didn't change, and I still compute the bad hash. Like I can't structurally cross the loop. Now the field will say I contain a value which happens to be a type pointer to a struct, and he gets all the way to the struct as I'm running my fingers around a cycle here. He gets all the way to the struct to get his hash bits. And then everybody always caches all their hash bits after the first compute. And they always assert if they end up getting asked to compute again that they get the same answer from their hash function. So I know I don't have any mistakes about how it's computed. And it's constant time, 1 bit to, And unrelated to everything, I have Meet the Coffee Coalition for Racial Equality from Phil's Coffee showed up on my email pop-up. I'm like, huh? Funny word coffee right there. No, never mind. Yeah, so it's just I slice the loop, and then somebody has a bad hash, and that led me down the path that Cameron's talking about, where we try to get a better hash function out of bad pile of bits.
Did you link to the paper or the thing? Or
I threw it in the chat. Yeah.
Is it the lookup one or what?
Yeah, look up 3.
Oh, okay. All right. Okay.
Yeah, from there, I think he went on to a somewhere I got a longer discussion from the dude. He has a pretty good discussion already about where you get the bits and how they get mixed. And it's all comments in the code. It's already pretty straightforward. I have a utility that is just cut and paste from here that basically says, if I know I'm computing a bunch of hashes incrementally across a structure, like a structure is doing field by field by field, I call this thing, which partially adds with state so that the fields in order 1, 2, 3, 4, 5 get different mixings, because you get a better answer out of it than just being order independent. And then there's a close it off and give me the bits. And they're all things that you can do in, you know, half a clock to 1 clock with counting x86 wide issues. So they're all super cheap. Certainly compared to the cache miss that you get when your hash function sucks and you're off onto the linked list of the wrong guy. And instantly my hash table went from this horrible exponential distribution where some set of buckets had 1,000 entries and many of my buckets, I doubled the table periodically to spread things out and they weren't spreading because they all were hashing badly, to like almost completely flat. And then you get a little bit of a rise on the histogram. Some guys get like, one guy gets 10 entries and a couple guys get 3. And the average probe now is 1.1, which, you know, is about darn as good as you can get. So I don't know. There's a lot of annoying things going on there because I ended up holding on to partially built cyclic types that I have to compute a bunch of shit before I can close the cycle. So the type building infrastructure is annoyingly complicated, but I think it's theoretically sound. And if you stare at what it does and how it works, yeah, I don't think there's any shortcuts I could take at this point without sort of reconsidering my entire world on cyclic types.
Sorry to repeat, but what happened to approx?
Oh yeah, you missed. I gave up on approx. It was I spent a month at it.
I gave it a go. I have a few ideas, but I don't know what when I can test them. But basically, I think you are wrapping the types in order to get to the. We should do the exact opposite. You have to compact the type since it is cyclic.
Yeah.
That's basically if we have to cite the simple sub, the mu type. The mu type is doing exactly the same thing. It come up with a new type, and it constrains the new type to be a super type of what the right hand side of the type would be, of the recursive type. But I have to explore to test if it's basically you have to have a type ref. You have the type to refer to something that is not yet known in the type system. But I have to try to.
Yeah. Okay. So I mostly have all these kinds of things. Like if the type system has something, then it knows what it is, but it knows it very weakly. And when I'm building like a type for a struct, then the struct gets, I give it a number, it's the alias number, whatever, fine. Okay. Just as a hook to say, okay, this is its name since I don't have a name on it. And then I can say things about it like, hey, this points to a struct, which contains some fields that I discover. Okay, whatever, fine. So now I'm looking at my program analysis and I'm doing basically partial evaluation along the program, and the program is self-recursive and it's calling new instance of the struct. And the expectation is I'm building a linked list. That's the sort of the common canonical case.
Yep.
And the wrapping point where you're building a cyclic type has the problem that I can easily show where it fails to be monotonic unless you become very aggressive about how you chop shit off, and you lose all kinds of interesting precision. Yeah. And then I have a lot of test cases I can step you through.
I repeat, I have a few ideas that I can try, but I don't know when I can try them. But basically, you have to refer to. If we take simple sub, for example, the minute you encounter a type that references itself, it wraps it into a rect type and basically stops there.
Right.
Later, when this type is, it come up with a new type term that is constrained to be a super type of the right hand side of it.
You're dealing with a constraint model.
Something like that before it can compact it back to something that can be unwrapped unlimited times, like linked list. That when
okay, so I'm not having a problem getting back to the compacted type because my cyclic types are exactly that. They are the compacted version. Okay. The problem is that in an arbitrary type graph, not necessarily what you can build with simple subs, whatever algorithms. In an arbitrary graph of types, I can show that you can't maintain monotonicity without doing something, various ludicrous things. And I'll give you some counterexamples that are pretty small. I have the test cases. You'll have to translate them to whatever you're doing.
Yeah.
They won't map naturally because it's monotonicity versus constraints.
Okay.
So it could be that the constraint model gives you an entirely different approach that, drops monotonicity as requirement, and you get a different answer out, and it's okay.
Later, a simple sub have some mechanics to compact these constraints to simplify it to a known type. Here, I agree. If you take the previous example, the last week, with the while loop, you unwrap it n times, and basically the first type is some integer. If you compact it, you don't know how big the integer is. You cannot, like you said, you cannot pick the most precise types because you keep it compacted. It becomes something
compaction represents the approximation of the infinitely unrolled series.
Yeah. Okay. And that compaction is, you cannot guess it if you keep the type compact. You have to either unwrap it if you know how.
Okay, so let me make sure we're tackling the correct problem.
Okay.
So where I have the algorithms right now, the compaction step, there is a version that says I'm going to approximate lose information, and then there's this compaction that just represents getting me a canonical answer that's exactly the same as what you started from. Yeah. So the canonical answer version I have perfectly well theorized, well tested, well working.
Yep.
So I never have a problem if I'm not actually losing information to get back to the unique compacted type.
Okay.
So this is all about when and where you decide to lose information in order to do things. So the other piece of that is all the unrolls and then meet and then recompact precisely. Those all work, and they're stable and they're safe and they're good theoretical, yada, yada.
Okay.
This is all about, I have two different things I have to claim. I don't know which one I'm getting, so I have to somehow meet them together. They're both cyclic and infinite.
Yep.
And what is the approximation that I want to use here, and how much information do I lose? And do I maintain some sort of monotonicity property so I can guarantee that I'm going to run downhill and hit a fixed point and be done?
Yeah. Okay.
So it's all about where you're losing information and how much you're losing.
Yeah. I can certainly think cases then when you can one type is unrolled some amount of times, and the other type is just represented as a recursive type, and you have to align them somehow in order to approximate it.
Yes, but say the actual act of unwinding and then rewinding in order to get the meat and the fixed point. If I don't lose the information in that step, I have that working just fine.
Yeah.
Let me pull out some bad looking code here. I'm trying to find the simplest example that might give you the feeling, and I can give you the comments for the really ugly examples going on here as well. Here's a test case. Let's see, these are all like turned off because they all failed out for one way or another. Let me go throw test case in the CCC doc and see the kind of things I'm looking at to begin with.
Okay.
So there's some setup to go. Then there's like, I make some new bit alias. So that just means I've got two different structures I'm dealing with. It turns out I have a third one that's a hack for strings. That's what the string hack's going on. I build some fixed fields that contain some values. One of them contains a string pointer. One contains a X scalar or a high value. Then I have to build a cyclic type in Java. So I build a bunch of structures. I stop and I install it. It's annoying. I don't have a better answer because I can't build something in Java without first defining something that's not complete and then completing it. Also, the cyclic things I built, I typically hand build. I don't ever get the minimal. I don't want to try to get the minimal. So the install minimizes for me and gives me the exact same thing. But I can be stupid about how I built them.
Okay.
And then I come along and ask some approx question about the thing. And this one's actually not giving me the question. I might find another version, but I have I'll put some comments out here instead of code. If I find where's the good big one here? Those are too easy. Where's the ugly one? That's getting there. That's the tree one. These are all in AA's test approximation file. There's an infinite loop building one. Where's the, I thought that was number 4. I can't find it. I'm feeling stupid. Here's some comments for an unrelated test. See the kind of thing I'm doing here. I build a type pointer which has an integer and a pointer to a structure which has an integer and a pointer to, and a structure which has a float and a pointer to, and a structure which has a an int and a pointer to, and then I wrap it P1 here this cycle. And I build these things as cyclic types, and they go ask, hey, what's your
infinitely okay? Of course, you always come up with a type that varies its type too much. You cannot approximate it unless
right.
you.
So the question isn't, can I mean, I have to approximate here. That's fine.
Yeah.
What do I get out of it? And am I monotonic? This is not the failure mode that you were looking at. Oh, here's the shorter comment for one of the uglier guys that I did a big old test case on. Here's another. Here's another version.
Right.
So this says I have some structure A0. It points to some X's which are mutually self-pointing. They each point off to an A type, which is different from an X type, which points to an X, which points to an A, which points to some mutually things, and yada yada. And now do an approximation where the count of A's in a row is limited to 3. And yet you maintain some amount of precision at all, whatever. So I have, what I'm trying to show here is I have a large collection of these things where I build sort of arbitrarily complicated, this points to this, points to this types, make an approximation out of it, validate the approximation is monotonic.
Okay. At this stage, you can always come up with a type you cannot approximate, because it's you can infinitely nest it deep. And
no. Suppose I only hand you finite types to begin with, other than they might have cycles internally, but
you can try to somehow approximate it at a given depth.
Yes, this was from the original cutoff depth of 3. Code I wrote and tested, and then I discovered I couldn't do it at 3, and then I backed off and said, can I do it at 1? And then I threw away the cutoff for depth things. Can't do it at all. And I kept simplifying my problem and saying, can I get this at all? And when I talked to you guys last week, the answer was, I don't currently have a way to do it at all. Never mind getting fancy about depth things. I
don't think we will be able to come up with some kind of approximation that preserve the things you want from this type.
So I limited my things I wanted down to the 4 I mentioned last week. It's shorter, so it's not, so it will take an infinite thing and bring it back. And I never have infinite, obviously. Instead, I have something I grow, and then during partial evaluation, then I need to shrink it back, and I grow it in partial evaluation, shrink it back. So it needs to form a stable fixed point under the operations where you do a small fixed amount of growth and then approximate. But
first you have to find where the type recurs. You have to find at which point the types become cyclic. At first you have to find.
So I'm never given the cyclic type up front. I'm given, I've made a pointer of flavored A to something, some fields. One of the fields has a pointer to flavor A. And if I run through the partial evaluation cycle, I get a pointer to a pointer to a pointer to a pointer to, they're all, pointed A, pointed A, pointed A, infinitely long, and just grows up bounds. At some point, I can easily look and say, I see 2 in a row. I have a pointer in A, it has a field, maybe through some other unrelated pointers, B, C, D, E, I don't care, back to pointer A.
Yeah.
Okay, right now I've got 2 A's in a row. Time to approximate.
Yeah, it's from this point on, it counts as a recursive type.
Yeah, and at this point on, it's counts recursive, which is all fine. So I'm good at that point. So step 1 has to approximate. 2, it needs to be self-monotonic, meaning if I take a type and then I take the approximation is strictly lost information. Right? It might have not lost anything if the approx is a no-op, but it can only lose. It cannot magically gain information.
If you gain information, you're not approximating.
Yeah, right, exactly. Yeah, there's something else going on. But the other one is that if I have two guys who have an is a relationship between them, their approxes have an is a relationship between them.
Of course.
So I can't take a guy, lose some information and approximate it and have something more than what I got if I approximated here. Right?
In your roots, you have to be monotonic. You have to maintain that relationship, either be more or less precise. You have
right. And then the last step, of course, is I just want you to not suck. Well, that's loosey-goosey, but the easy answer is every approximation step throws you to bottom, and now you're monotonic, and all your approxes are monotonic to each other, but you lose everything. It's all gone, and you got nothing.
At first glance, we have to just restrict ourselves to a simple recursive type, like linked list, like something.
So I gave you examples of simple linked lists that went 2 layers deep, but they had other things floating about on them that had, they had a field, they had a payload field, and they had a link. And if you scramble the payloads up and down relative to each other, and you ask for the approximation, you have to maintain monotonicity. And that was where I started to find that I actually couldn't reliably do it. I could maintain the correct properties if I didn't approximate, because it was like I could always slice something thinner, infinitely mathematically thinner, and get you in between two things. And this would give you the downhill property, but it asymptotically went forever. It never approximated. There's always
it never stabilizes.
It never stabilizes. There's always another place to slide another guy in between, and that's what you're using to maintain monotonicity. So
I sort of gave it. I sort of got the picture now. Okay.
Okay.
So approx is going home.
so I killed approx, and that meant that a bunch of places where I would have had interesting, precise information about what is in a struct, I lost. Or what it really means is I lost it all at the pointers. All pointers are shallow. I only know that you're an alias 5 pointer, an alias 6 pointer, you're point to a Bob or a person or a cat or whatever, but I don't know anything about otherwise.
I would say that's a fair sacrifice, because.
And then at all the points where I want to do interesting analysis, I stop at that point and I build a sharper version of what it means to be a Bob or a cat or whatever I'm pointing at, and then use that in my analysis. And that work has been going on all this week. I found a bunch of places where I failed to go back to the basic structure, and I had to go get it. So I had to add places where I probed things that I didn't before. I then had dependencies where if some type changes that's nested inside some fields, other people who are now probing deep will discover it, but they need to go back on the work list in order to do the math and discover it. So I had a bunch of progress bugs. So all this last week I've been, and then I had bathroom fails I've worked on this week too. So
I got.
Go ahead.
Yep, go ahead. Sorry.
I was going to ask what the interesting analysis was. You said when you do some interesting analysis and you want to go deeper.
It's all partial evaluation steps. So I'm coming along and saying, I have a field. He asks for the X. He's called X. He's got an incoming pointer. He wants to know what is this type he's going to have. And then I'm going to confirm that at the next step, right? So that's sort of the level of interesting analysis. So X says, what is my pointer? Okay, my pointer is a shallow pointer to a Bob. I'm probably an X field on Bob. What's a Bob struct? Okay, he didn't get it from the pointer. So he goes back to the Bob structure in the code, chasing that Bob name or the alias 5 or whatever it is, and asks, do you have an X field? Oh, you do. What is your type, Mr. X field? And then you get dependencies to the code that way. And it's still all monotonic and running downhill and hitting fixed points and shit like that's going on. It's all good in that sense. But now I used to have a dependency between the X field lookup and the incoming pointer. Now I have a dependency between the X field lookup and struct Bob with his X field. So the dependency chain got further removed. So when Bob's X field changes, all X fields in the universe that may have ever seen a Bob have to get updated. Right. So this is, SSA, linked list, whatever, however you want to do it. There's some way to say, make these dependencies obvious, and they're lazily discovered on the fly. And I used to do it a different way. And now I have to go manage dependencies differently. And Aaron asked me a question. Oh yeah. What is the type? Okay. So Aaron, in your question there, what is that type? You can, if you have it go infinite, then the infinite type is your infinite type. If you want to make an approximation that's cyclic, And in your case, actually, if it's
I feel it's like it doesn't have to make the choice.
it's not a
It
choice,
knows
it's an and, not an
Yeah.
or, right?
Yeah.
Yeah, so you're arguing that you're making a cyclic type, which is fine. As part of making the cyclic type, you approximate and you lost something. What you lost there was the distinction that it's alternating between B and C. So here's another cyclic type that might, you might be more excited in, that loses less information. And this probably should be in the doc. So that's one that says, I have an A, I have a B question mark, I have an A, I have a C, and I'm repeating back to the first element.
That's
So
my
I do retain that it alternates between B and C every other A. So both of these are valid approximations. Which one you want to keep is how much precision you want to retain. Do I care to know that my linked list is alternating payloads every other step or not? In the land of Java and in most languages, you don't. You immediately take the union, not the intersection, of B question mark and C, and that's your payload.
I would say if we have the run types, it have to be either B or C, because you have to distinction at the runtime level. You have to know it's either B or C.
Yeah.
But your example is known at the type level that first is B, then it's C, and then recurse again. It's known at the type level which one types come next.
Yes. So the usual story is that the type that Aaron wrote lost some information, and you have to put a runtime test in to regain whether you're looking at a C or a B question mark.
Yeah, the whole point you have to the type to know as much as it can at compile time, so we cannot carry back to the runtime.
Well, that's a performance hit, but it also means you had to write code that said if payload is instance of B,
if it doesn't know,
else cast it to a C.
If it doesn't know, it forces you to check.
You have to write code to check that says, oh, I must be an instance of a B and also I'm a C, and maybe I got tagged unions that I can tell by the completeness that it's a C or it's a B, but I had to put a test in my code that said, this is what it is.
Yeah.
Whereas in the second case, you had to unroll your code because you had the incorrect types for the B and the C. But if once you unrolled your code, the analysis was correct.
If you have a term for this type, it knows that if you select the second, it's B. If you select the fourth type, it's C.
It's C. Yeah, exactly. Yeah. So the use case here would be, I can say a.val and do B like things. A.next.val. I guess A.1 next val, and known as a C here, and do C like things with it. And in the other case, the .val field has no distinction. It's B and C.
So it can prove that it's B and C, and so it can eliminate the check. You can work.
And I think the other major takeaway is that there are multiple different approximations that are possible.
Yeah, that's a fine distinction between compile time types and runtime types.
Well, I'm looking here at I want a theoretically good approx that has those 4 properties. And in the case of distinguishing between the 2 that we talking about here, I kind of don't care. Neither of them suck. So I'm okay with either of those.
Okay, so this is the state of approx right now.
This is the state of approx. Yes.
Okay. We can
backed off from approx after a month of trying to make it.
Okay. If I come up with something, I will.
I'd be very happy to push it through the test harness. Help you set up a test harness where you can repro the failure modes.
The future is a little grim, but who knows?
Yeah, well, the nukes aren't flying yet, so maybe we're still alive next week. Okay. Jesus Christ.
Okay. That's fine. We can change gears right now. We haven't asked a question in like 10 minutes, so okay.
I have a question. So like the hashing for the circular references stuff. So can't you like take each strongly connected component and then like say, I'm going to take the list of all the nodes in the strongly connected component in some well-defined order and hash that, and that'll be
right.
that'll be the hash of the component, and then
Yeah.
you compute each of
Yeah.
the node passes. using-
Right, exactly. Okay, so what really happens is that I don't know I have a strongly connected component yet. And I'm building this thing incrementally on the fly. And I want to hash as I go. And I'm going to find the close that makes this into the cycle and makes a strongly connected component using a hash to find the last guy and the first guy where he went to via the hash. So I don't have a strongly connected component yet. I'm fucking building one. Or not. It may end up being not an SEC in the end. I don't know yet.
And part of the problem, Alan, is that none of the languages with their standard libraries have any support for what you just described. So look at the vast number of stateful parameters that are passed to hash code in Java. I'll give you a hint. The number starts with and ends with a 0 with nothing in between, right? There's no parameters, there's no state, right? So you can't do graph traversal using the standard API, which means now everything that composes that hash, you have to invent a new interface to carry that graph traversal eternally cyclical,
not
logic.
structurally recursive.
So yes, it's certainly possible, but you're basically reinventing everything.
Yeah, and that's kind of what I ended up doing.
Yeah, I mean, it's the correct answer. So Alan, you're right. It's just that nothing helps us do it. How's that
Maybe it's time to introduce one of the features of my language that I actually really like, which is it's basically dynamic scoping. So like you can define a variable in a function, and then you can use that in like any function that you call.
Yes.
And so
basically you're creating a magical scope from which you can pull state without having globals.
A context for the function.
Right, but nestable, recursively safe, and so on. Yeah.
I end up doing similar behaviors, like very indirectly, but I'm getting the similar effects out. The usual story for these things is everyone has a unique ID, and I have a bit set I'm using to walk and validate that you're closing your cycle because you visited it already. So in the land of no cycles, but a DAG, and I'm doing structural hash codes, then you build it bottom up, and the visit bit is the hash was 0 or not 0. I have a hash field. I set it the hash is guaranteed non-zero. That's an invariant I came up with. If I see a 0, you haven't had your hash computed yet. I recursively compute your hash. You set non-zero now. It's forevermore 1 clock to go validate that you have a hash and non-zero. And you build up a recursive type that works really well. And a recursive hash works really well. It's all efficient, fast, cheap, blah, 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 blah. All this fails if you might have a cycle.
Then you use Tarjan's algorithm.
No, that's what I'm saying. So the next step is I don't know that I'm going to build a cycle or not. So I like the recursive building thing. So if you look in my code example, I say type recursive meet plus plus minus minus. That's me saying, and here I might make a cycle, stop doing recursive things, but I'm going to have an API that builds recursively. It just means that instead of interning things as they come, I know they're not yet complete. I'll stop at the building the hash at the struct, which will show up eventually in here, or it was all cheap and I didn't care. And when I do the install step, I'll take everyone I can reach, doing the SEC algorithm from Tarjan, yeah, absolutely, and computing all the right hash things and get it done. But in between, while I'm building it up from what I don't know I'm going to have a hash or not, I need a hash of the moment. And that's part of the difficulty of the whole operation.
Oh, I see.
So I have some code that's in between the recursive plus plus minus minus. And in there's shit that's going on that's basically saying, put a thing out. Typically the answer is immediately upon making it, I probe it in the hash table, I intern it, and I get back its canonical answer, and forevermore it quality checks or a pointer quality in 1 clock cycle. And I'm done. And if I threw the one I just built away, it goes on some cheap, efficient object pool recycles. It takes very little time and energy to build them structurally recursively normally. If I suspect a cycle is coming, I have to stop the building process at the point at which I build a hollow shell and somebody doesn't have all the fields filled in. So I want to be able to build with an API that's the same API, and then at some point say, oh, this guy takes a null for a field that's not valid elsewhere. No one else can do that. And then he has a hash yet, even though he has a null field contents, which are otherwise, you know, at not null, API, whatever annotations. And I'm alive and well, and then I do recursive things actually with things that I know have already been interned. So I can talk about things that have interned already. They already have the hash code. I take all kind of shortcuts for them. There's optimization steps left and right where I, you know, can recognize the situation's not ugly, but then I end up filtering back to the ugly situation, and I have a bunch of things that I don't know yet. And at that point, you say recursion meet minus minus. The install step validates like all your hashes didn't change, all your pointers got filled in, they're not null. I'll now build SCCs. There might be a collection of independent SCCs, and I'll figure them all out. I'll put a shortcut bit on all things that have an SCC saying you're part of a cycle, because my equality check, if it's the already interned one, is pointer bit compare and you're done. But the equality check, if you're not yet interned, like the interning process itself needs an equality check, says you're part of a cycle. You need a cyclic aware equality check, right? Because I built a cycle. It's a wheel of pointer to pointer to pointer. What's been interned is members of the pointer. What comes in is one member of this pointer of this cycle. He has to match with some other member that's of an unrelated cycle. So you need a special, I'm a cycle aware equality checker. That takes advantage of the shortcuts when I've already been interned, and you know there's graph leaves piling off from the cycle in all directions, some of which have been interned and have the instant one clock check, some of which lead through complicated shit you don't know yet to another unrelated cycle. So that all, I mean, I have it all now, but boy, it's a big ass pile of work, and it's just non-trivial as you. There's some stuff there, yeah. And oh, and then the next thing is, when it's done deciding I have the SCC, I now want to know that you're actually canonically equivalent to, you need the minimization step. So if I built you a closed cycle that was A points to a struct, which has a next, which points to an A, and I gave you another guy, which is an A, has a next, points to struct, which has an A, which is a next, which points to struct, and it's a double unrolled cycle. These two are equivalent in that nobody who walks any path of the same chasing pointer to struct to next field any number of times can tell the difference. So difference that makes a difference should be no difference. So they need to hash the same, and they need to pointer equality the same, and intern the same. So that one you need a DFA minimization algorithm. So after you build the SCCs and you do all the other easy shit, you stop and you run DFA minimization.
Okay. Yeah, I found a paper on like minimization of trees that like it says it does it more efficiently
For trees?
Yeah.
Trees are
See, I don't know, maybe you've already read this paper, but I mean
trees you can take other shortcuts on.
No, this is regular trees, so it's infinite regular trees. So that's what you get when you have cyclic things.
Oh. Okay, I don't have only infinite trees for types, which I can believe you. But the Ullman algorithm there, Hopcroft Ullman, it's in log n. It's not too bad. I mean, it's ugly complicated in the implementation. If you want to be efficient, blah blah blah, it's ugly complicated, but it's not itself asymptotically inefficient.
Yeah, no, so this, it says equality testing is constant time.
Right.
So.
When I am done, I have constant time equality checking, but I'm not done yet until I can take an unrolled cycle and compare it against a tighter rolled cycle and declare them the same.
Yeah. So I don't know, maybe you're already implementing this paper.
Well, I don't have anything that's special about rolled trees, which I know have more structure and you can do shortcuts with. So like I want to know that I have a thing that wraps like this, and I'll put an equal question mark equal. Is this equal? I guess equal. This is to this. A to dollar. Are these two equal?
Are you in the doc? Or the...
I should put that in the doc. It's the chat in the doc. So this is the question. Go find the doc in my land of tabs. I rolled by it, I guess.
Equal how? The first question would be.
Yeah, well, so what does it mean to be equals? Here, I claim equals is, there is no path you can walk through the two structures that will tell them apart. So there is an in-memory layout where I have one structure on the left with a pointer to itself, and on the right I have three structures in a row where the last one points to the first guy. They all have an A field of some kind, maybe whatever. All other things, all edge labels are the same, all node labels are the same. You know, if you're struct, all your fields are the same, yada, yada, yada. It's all the same, except that one has three structures, one has one. Now, what's a path walk mean? It means I did a series of loads, like a standard everyday C style field load. I got something out. From there, it was a pointer. So I grabbed a field from it. I took the next field and the next field and the next field. And after I took the next field any number of times, I stopped, took the value field out. Okay, can I tell the difference between these two? If the answer is I can't tell the difference between them, there is no difference. And they should be given the same. So in the tiny example I give you, I want those two to be cyclically equals.
Yeah, type equals.
And that I'm going to declare cyclic equals to be type equals. Or type equals, I'm implementing type equals with cyclic equals in this case.
Yeah, so
Although
like,
in this case, the number is swallowed because it's infinite, right? One of them's infinity, the other's infinity plus 2.
They're both infinite in length. One will be multiplied by 3 and not plus 2. But they're both infinite in length. Yes.
The second is just unrolled 3 times.
It's unrolled to 3x the rate of the first guy.
So if one of the A's became an optional A question mark, does that
Yeah, as soon as
change
you,
the
as soon
answer?
as you change the labeling.
Yeah.
So putting an A, making one an A question mark changes the label. As soon as you change the labeling, they're not equivalent. So I'm not doing an approximation here. I'm asking a different question.
But if all 3 are A question mark, you'd say they're equal again.
Yes. So I'm just trying to say in a totally precise, no loss information way, are these two structures the same? If they are, I'm going to intern them and make them the same so that at post-interning step, I can just do pointer equality and walk away. Pre-interning step, implementing the interning step, I need to have a cyclic equality test. And how do you declare these two things equal in general? And now you can go ask the interwebs, hey, how do you compare two infinite structures for equality? And you'll get shit like tortoise and hare algorithm. You can go look up tortoise and hare algorithm. And I have the slightly more efficient version than tortoise and hare algorithm running along in here, but you get stuff like that going on.
I've only used tortoise and hare once, and it was for a job interview question.
yeah, well,
Yeah,
so
exactly.
okay, I really think you should read this paper then, because I mean, what he describes is actually how to compute the best graph representation for a given tree with cycles.
Okay, so again, I know you can take shortcuts if you have trees that are infinite. I do not have trees that are infinite.
No, they're like, so a tree with an infinite tree is a graph with cycles. Okay, they're like that. I mean, they're the same thing.
Okay,
basically.
I'm not following because I can clearly write you a clique of unrelated types that all have pointers to each other in the arbitrarily large clique. It ain't no tree, but it has cycles, right?
Well, the reason he uses the term tree is because you have a root. You have this. You have.
Okay,
You have
I do not have. Right, I do not have a root. I do not have a root.
You have the out. It's a type. You have the outermost part of the
I
type.
have picked an arbitrary member of the infinite list as being the pointer of the moment for the root, but they're all equivalent to all other members. So it's an infinite row. It's unrolled infinitely. Somewhere in the middle, I picked a dude arbitrarily. You're good enough.
Right,
Okay.
and that makes it a root, and that turns it into a tree, an infinite tree. Because you could do depth first search and get a tree structure from the.
Okay, if you do a depth first search, you're imposing a tree. Well, yeah, as soon as you do depth first search, you already added an inlogging algorithm, but you do DFS and import a tree over an arbitrary graph. I'll agree to that one. That's what I have. I have arbitrary graphs. You can put a tree over an arbitrary graph with depth first search. That's fine. In fact, I do that any number of times.
Right,
I have all kind of fun questions like, how many times do I see A's in a row before I see interesting cyclic behaviors or not? count the number of times I see A's in a row, ignoring back edges. Well, I imported a tree over the thing by walking a depth first search.
Right.
Yes,
and
I do those
so
already.
what's in this paper is like these minimization algorithms
Yeah.
for compacting the graph to its smallest.
Yeah.
round.
The canonical one is,
So if you do it on your A example, for example,
Yeah.
it will turn that right type into the left type,
right.
which is what you want, because then you
Yes.
can say, oh, they're equal.
Here's the trick I'm trying to get at. You have to beat in log n asymptotically, or I don't care. You have to have a super low constant that's exciting, or you have to beat in log n. And as soon as you said I did a depth first search look, you're not beating in log n, so I don't care.
Well, no. The point is that it's incremental. So like you can maintain, you can build up the types incrementally, and that's
Yes.
what the algorithms are. So like he
Okay.
doesn't. So like even though like you think you're computing a DFS and you think you're computing all these expensive
Right.
algorithms in the graph, but what you're really doing is you're just doing a small number of pointer algorithms.
Yeah, you're doing an incremental build over a structure, you know something. So it is commonly the case, I'm doing an incremental build over something I know. It is commonly the case that I optimize the shit out of that incremental case. It is also commonly the case that on the big examples, I make from whole cloth large type structures from whole cloth that happen to be cyclic. I do not incrementally build them up that way.
So yeah,
During the partial evaluation step, I start with something. During the approx version of the evaluation step, I'll start with some fairly large complicated type. I'll do an incremental add on it to make it a little bit larger, and then I'll prox it. And the approx step got complicated while I was trying to make it have the right properties. Building an STC was not the issue. Does that make sense? Like this now, put the link in. I'll take a look because I am doing everything
already put it
incremental.
in. I mean, so like what it is that the building it takes order n time, and then testing equality goes from n log n to constant time, because you're always working with this minimized representation.
Yes, that's exactly what I'm doing now. In the sense that as soon as I'm done,
construction goes a bit, it gets a bit when you're building like order n elements, that goes to order n squared though, because you're not you have this overhead that you're minimizing at every step.
I am minimizing at every small step. I am incrementally extending and minimizing. In the absence of cycles, I clearly do it in constant time. I end up with a pointer equality after the minimization step. That's constant time. That's the whole point of the minimization step.
Yeah. Oh, never mind. I wasn't reading the paper. So what's expensive are loops. So when you build a loop, that's what's in square.
Yes. And then as soon as I've accidentally built a loop, because approx wants to make a loop out of a thing that was not loopy, I now have the in-log in algorithm on the body of the bits that are the approx is visually hacking on.
So.
Yeah. I mean, I got it up. I'll read through the same thing that's new and different.
Yeah. I spent a lot of time digging out that paper from the literature when I was.
Yeah, it's the right kind of stuff.
Yeah.
What is it? What year is it from? 2004. Okay, it's a modernized version of something maybe.
I think it was. Oh, it was.
So he's got trees with back edges, which as soon as you go to arbitrary cycles, I bet you it doesn't give you any asymptotic savings, except he's doing an incremental update. I'll look and see if he has an incremental update version.
Let's see. So it was mostly his PhD thesis, which was 1999, and then he improved the representation in 2000, and then there was a 2003 paper.
Yeah, it's fine. One of these is fine. I mean, for me at least, I do so many graph algorithms that just in the back of my head, I know what the hell goes on all the time.
All right.
I'll whip through and see if it's got something new on incremental building. I don't have any strong theoretical results on my incremental building. I know that the strong thing I can say is if you're not got any cycles, I'm doing the obvious constant time thing. soon as you have cycles, I whip it out, and I don't believe it's n squared. I believe I am n log n. But I do the n log n step, you know, every pass around through my partial evaluation, which means you're headed for n squared if you can't limit your fall step to some bounded time. So that I want my approx to like cut you off and say, quit growing, you're now a cycle. And that gets us the whole, what the hell to do about approx. So my current state of the world, Theodore, is I yanked approx and I'm running without it. And I don't know, it should, in theory, you know, knock on plastic, behave as if I am doing an approx of depth 1 only every time.
When you say yank approx, do you just mean for structs
Well,
and tuples, right?
That's
You're still
all
doing it
approx
for
ever-
ints and primitives.
Approx was uniformly could be applied to any arbitrary structure. However, it only did exciting things that structs that pointed to fields, pointed to type, to pointers back to structs. There's a separate approx that has functions that point to themselves. That's a special tiny case that can be solved because there's no fan out. But for structs that point to fields that point to have pointers to structs, approx does something, and I yanked it for those. Basically, I had been calling approx every time I do the partial evaluation step where you ask a structure, what is your type, Mr. Structure? He says, oh, I'm structurally recursively built up from the contents of my members. So whatever my members have, I then wrap that in a new struct. Okay, well, my members have fields which have pointers to the last time I came through here, and you start getting this infinite growth. And I yanked approx there. And instead I said, pointers are always shallow. I have a pointer to a person, a pointer to a cat, to a dog, to a car, to a number 5 alias, to a number 7 alias. I have a pointer. Okay. Now when struct comes along, he says, I'm composed by members which have fields. The fields themselves have types, which one might be a pointer, but the pointer is shallow, it doesn't go anywhere. So I don't need to call prox in the struct.
I think it would be correct to say this version without approx is just nominal. You lose the structure of the type.
You lose the structure of the type, yes.
Hmm.
You have a shallow version, so you don't get any cycles.
You can look it up by name though, then, right?
Always, yeah. I give everybody a number. I look it up by numbers instantly. Fine, whatever. Yes, you can look it up by name. By name. Sorry, let's just say by name. I have a lot of anonymous structs, so there's no names. So fine, but there's a number. Yeah, whatever. You can look it up. So, and then what happens later is I have a field that wants to load from a pointer. The pointer is shallow. What is the type of the field? He doesn't know. He has to go back to the struct where he came from. So he asks the pointer, what are your aliases? What are your cats? You're an animal. Your cats and dogs or horses and animals or whatever. And he goes to those structs and says, do you have a leg count field? If you do, this must be a load from you. And therefore this is my type. And it's the union of the, it's the meat of the aliased guys. And I ask the question incrementally, step by step. So my thesis is that doesn't change my asymptotic running time, and I still run downhill and get an answer. And mostly all my tests are passing, and I have a couple of cases I'm still sorting out where I've screwed up something.
Can I ask why did you want to keep track of the extra information if you could look it up?
Because it's more efficient,
Okay.
because it's easier to understand the algorithm. If a pointer was deep, it says, I'm a pointer to an animal which has a legs field, which is commonly 4, but might be 17 or 1,000 for a millipede or whatever the fuck, I have some information there. Okay, when I look at the asymptotic running time of the algorithm, the field for a load of leg count gets one input, which is a pointer. And so if the pointer changed contents, the legs went from 4 to int 64, int 256, then I know I had to go update this guy. And this is an adjacency relationship in a graph. It's a neighbor, it's a nearest neighbor algorithm. I change an element, I go to his outgoing neighbors, I say, y'all need to recompute. Okay, so this gives me a trivial algorithm that's totally a work list, runs really fast, efficient, has asymptotic good properties, fine. Okay, now instead I have a problem that says, this guy here says, oh, my pointer picked up an alias. This is the easy version. I picked up an alias 7 with my alias 5. I picked up cats to go with my animals. So now I go to animals and cats and compute something. So I had to go to a couple things, as many as I have aliases for. So that's a little less efficient, but maybe I can bound that. But the real problem is that animal changed from legs of 4 to legs of 1,000 because a millipede showed up somewhere else. So animal doesn't know shit about where the legs are being asked, because there's no pointing relationship. There's no graph relationship between them, because the animal pointer got passed along and passed along and passed along. And much, much, much later, I pulled out an animal-like thing and I asked, what's your leg count? But I don't know what's an animal-like thing, because I'm doing type analysis to discover that it's an animal-like thing. So somewhere down the line, this leg field load says, oh, I depend on an animal over there. It's not longer adjacent in the graph. So I have to do an adjacency thing, which is a lazily discovered, there's an interconnection between a def point for an animal and a point where I read the legs, and I'm discovering that on the fly. It's not apparent from the graph immediately. And so that adds a complexity to the algorithm right there. That was much the week was sorting out those kinds of bugs.
The reason you don't know it's an animal-like thing yet is because everything is inferred. Like
It's all inferred. You can add types, and I'll check that your types are correct. But I'm doing type inference.
Yeah.
Like Hindley-Milner says, you can do this with Hindley-Milner straight up, and you get the same exact situation. The first time you come across the legs field load, you say this pointer must be pointed to a thing that contains legs, and you begin to build up these type structures. Later on, that pointer came from, somebody says, oh, I'm an animal, I have legs. And you say, oh, you guys are compatible. Yay, no type error, right? Or, the animal says, I don't have a legs field. And this guy says, but you have to have a legs because somebody somewhere through some very long indirect chain expected a legs field. And then you get a type error. So I'm discovering those relationships. In the land of a non-Hindley-Milner, they're typically point-wise adjacent to the text that you write. So I can
that
do a
type
nearest
error
neighbor.
has a potentially long path between the place where you passed something in and the place where the assertion this must have legs is.
Yeah. Yes.
How do you tell the developer what went wrong so they can figure out which place in the code to fix when there's a whole path where it could be?
This is you're asking, why do Hindley-Milner error messages suck? And the answer is,
I was hoping to ask, how can you make
he was actually answering,
but
yeah, and I'm going to give you an answer that is as good or as bad as the standard Hindley-Milner algorithm suck. For error messages, you'll get an error message at the point where you said legs that says something like, but your incoming argument doesn't have any legs, and you'll be all confused. Why didn't this guy not have any legs? Well, if you took the inference from Hindley-Milner, you have to step it backwards to go figure out where you failed to have legs. The way I have debugged these in the past on Hindley-Milner style things is I start adding type assertions incrementally along the way, so that the distance between the fail and the two endpoints that are part of the fail gets narrower and narrower until it becomes obvious. My more common fail mode is, because legs is too unique, it's obvious what's going on, is I have an auto currying language. I fail to pass the correct kind of arguments. Instead of having the result of a computation, I have a function which expects one more argument, which will then give me the result I'm looking for. So when I come down and ask you, please, sir, is your number greater than 7? They'll say, I'm a function, I can't be greater than 7. And I'll be, fuck, you're not a function, you're supposed to be a number. How come you're a function? It's the same as in JavaScript, you got none is not a function. You're like, geez. Okay, now you have to go back and figure out where you failed. And so I start adding assertions. Well, this argument was expected to be an int, so I'll just tell the damn language, you're an int. And he'll say, you're not an int because you didn't pass an int to this function because of over here. And then you work your way backwards yourself. And the answer is yes, in fact, you cannot tell the programmer conveniently, you suck.
And once you're done with that debugging, you leave all those types in place?
Oh, yeah, usually, yeah. Now, sometimes I yank them if they're too egregious, but if I yank something somewhere, I almost always put a different one somewhere else that covers it a little nicer. So, where I'm at with this problem right now is that I am attempting to track all the endpoints where things come from so that I have a chance of giving you the correct answer. Here's a set of things. You mixed millipedes, cats, dogs, and animals And over there, you said something about, you know, pet name, and the millipede never had a pet name. So here's a collection, but there's a millipede in it and it has no pet name. Here's a set of uses of pet name. These aren't compatible. Decide how you're going to name your millipedes or not ask for the name of a millipede. It's basically, it's 2 points. You have 2 fails. It's usually just one or the other that you obviously going to change, but sometimes it's a collection of the one and the collection of the other, and then you have to like compare your collections. Jesus. This is like
if I have like 1,000 separate source files, is there any way to parallelize the type checker? Or sounds like if everything's inferred, it seems like, you know, any of those 1,000 files could depend on another one. Is it all like a one thread going around,
right,
finding things? And
well, like my current theory is that I'm going to have people will do modules, where a module is a closed set of typable things, and that you will put a type annotation. You'll be required to put a type annotation at the module boundary. I'll infer and validate that I love your type annotation, but that compilation is now independent.
I see. So the modules could be parallel. Each one could be computed in parallel.
Yeah. So it'd be like Java C compiling a package in parallel with other packages.
I see. Okay, that's interesting.
Yeah, to get parallelization within that, you end up having to basically create a state machine, you know, a stage-based state machine, so that you can have any number of endpoints. Well, endpoints at that moment in time that could make progress theoretically, so you could assign them to a thread. So
the analysis is a work list based algorithm that computes state on a graph. It is possible to parallelize such an algorithm, but the overheads would typically be much worse than you would normally expect to get out of just a single thread guy being efficient. So it's a very fine-grained incremental thing, which means that you take and release a lock on a fine-grained state, except you can't lock one guy. You have to lock a transactional region in the graph, do the analysis after you've locked it. Like you'd actually start doing the analysis and adding to your locks as you grow until you've got a closed set that represents a point where I can do an analysis. You flip the thing to the analysis results and you release the locks.
Yeah, the flip of that though is that you can still do it if you can poison. So if you can make progress and yet poison. So for example, in some cases you can learn something but not actually finish. You can't come up with a correct answer, but you can learn enough that someone else could use part of that information. So it's that's a more optimistic approach. Think in terms of concurrency and optimistic.
Optimistic. No, I know what you're doing. I mean, I do optimistic concurrency all the time. I'm trying to think of how it applies here.
Because we have to do it in our type system in a couple points where it's like we don't actually have enough information to tell you something about the type that we want to know, but we can produce enough information that you could use that to do the part that you need to know, and that'll actually be for someone else, and then I can use theirs to finish my part. So that's the type of thing we haven't parallelized it yet, but we could.
You could, right? I'm in a different zone in that I don't have. Like I'm a semantically shallower zone. I have these types, they're monotonic. They can fall in any order, they can fall in parallel.
But it's still the same, it's still the same general problem because you have recursion on a mutable data structure.
But if that monotonicity preserve the property, because if you compute this type, the type can only get more precise because you are monotonic. And in no matter order you switch the increasing of the information, the type can become more and more and more, because that monotonicity property buys you that you have to, I have some result right now, and this result can get better.
What I just heard you say was that the algorithm called Hogwild works here, and I'm wondering if it fucking does. That would make life a hell of a lot easier.
Interesting.
So Hogwild, so here's a variation. This might actually work. Holy shit. This is one that says I don't have to lock anything. I just have to read my region, come up with an analysis, but I cas a new type in. The new type I only cas in if it monotonically increases the type that he found there.
That's what I call this. That's what I call a state machine. A monotonic advance is the simplest form of a state machine.
Right. Because it's not really Hogwild, which can go backwards because
that's correct.
Learning can do that, but it is a monotonic. Yeah, there might be a way to do this in parallel on the graph. That's interesting. So that's the type analysis.
So
there's another one
Hog Ratchet as opposed to Hogwild.
I'm sorry.
Hog Ratchet as opposed to Hogwild.
Yeah, but it's not. I mean, people do these other things already. There's other older school names on this.
Can somebody throw a link? Hog Ratchet, Hogwild.
Hogwild. So I can go find Hogwild. So there's a deep learning Hogwild. Deep learning Hogwild. Yeah. Here is a
so that mostly works because deep learning doesn't care for the most part.
Yes, doesn't care. Stochastic. So here I have the paper link that's like reasonable, or I have a paper link if I find my fucking Git. Oh, there it is. CCC. Okay. Yes. So this is like stochastic gradient descent and don't lock, which lets you do fine-grained parallel stochastic gradient descent. In the case of the monotonic type systems, I guarantee forward progress. In the case of stochastic gradient descent, they don't guarantee forward progress. They don't guarantee you don't get stuck in local minima. But in practice, it's actually pretty solid. It's a good algorithm in general. Usually, it's not run in parallel. But the point they're making out here is that if you, on average, make forward progress down the slope, so it's hill climbing or up the slopes. You're hill climbing up a slope. And everyone's taking a step in different directions as they go. If on average, more people go up slope than down slope, you're winning and you'll make it up the hill. And the only reason you would get confused is because you looked at the local terrain and then you decided to step this way. And in between that look, somebody else was busy editing the terrain underneath your feet. And so you slid back after you stepped up.
The stochastic, it doesn't preserve the monotonicity. You can jump anywhere, but
gradient descent says monotonic. Stochastic says, well, not really.
Well, I will sacrifice a few thousand steps in order to give you a best result.
Right.
The best guess.
Right. And so their point is basically, as long as you are statistically going uphill, you don't have to be always taking the same path. Now, for program analysis, I need to end up at the same result every time. So I'm going to demand correct monotonic results.
Yeah.
In stochastic, you end up with a different place every time. It's like deep learning, you end up with a different place every time. But yeah, it's close enough to the last place, assuming your solution, your problem has a single good solution, you'll probably end up at it. If your problem does not have a single good solution, the stochastic guy means that you're going to not end up in the same one. Or if it has a bunch of them, you might be wandering along between the different good answers without stopping and settling on
some local minima, blah, blah, blah shit.
Yes.
That's what you want to avoid. Getting trapped in a local part of the curve.
Yeah.
Minima,
So, I did a lot of stuff with gradient descent in the deep learning, not deep learning, in the H2O startup. And so there's a lot of fun algorithm things you learned that totally have applications in what I'm doing now. In terms of the deep mathematics are roughly the same. What the hell is the right word here? My type systems doing an algebra over the types with the transfer functions are completely synonymous with how you take a gradient, generalized linear modeling, and you're walking up a slope to get to an answer. These have a very, very close similar mathematical parallels with the deep theory underlying them, roughly pointing to the same direction, doing the same thing.
Yeah, probably.
One of them is more quantized than the other.
Yeah, the same mathematical concepts are used in order to represent what we want to do.
Yeah.
Okay, next question.
Yeah, exactly.
Oh, so I posted this link pretty early on. It's destructor exceptions considered harmful.
Destructor exceptions. Where did oh god. Yeah.
Yeah. So it's this old post, And it's basically, as far as I can tell, this is the justification for why you don't throw exceptions from destructors in C++.
Yeah, I'm with you on that.
And so, basically says it's what it is you have a vector and it has an element with a destructor, and then you call the destructor in the middle of copying the array, and it throws an error, and suddenly, and so I don't know. So to me, this seems very unconvincing, because you can just catch the exception and hold on to it and keep running the destructors. And then, at the end,
somebody else throws, and somebody else throws, and somebody else throws. So you have a collection of exceptions.
Right. At the end, you have a collection of exceptions. And so you throw them all as an exception group, and then you're done.
Oh, you throw them as an exception group. Oh, that's interesting. Suppose I have a series of files that I'm busy writing on, and then I want to flush and close them all. And the disk got full halfway through the operation, and all the files have partially not yet written, and you can't write anymore. So they all throw disk full exceptions, and they're all half trashed now because they're all partially incomplete. And I get this exception group. Is that semantically, maybe it's the semantically good answer. Yeah, maybe it is. I don't know.
Yeah. So I don't know. So I thought I'd throw that out there. It just seemed, I don't know, the way I'm doing destructors is that they run before an exception gets thrown. So there's another issue in C++ where you run a destructor while you're throwing an exception.
Yeah. Right.
So that doesn't happen in my language because the destructor runs before the exception.
Well, the destructors are all nested and the exception is crawling the stack. So do you stop and crawl the stack and run all the destructors, and then you having crawled the stack, you now have the exception you can hand off? I claim semantically it's what's going on already. There's no difference here.
Right. Well, no, because if you think about it, if the function just returned, right?
Yeah.
What would happen is that it would run all the destructors and then it would jump, right? And so it's the same thing when you have the destructors and you throw an exception. What you do is you run all the.
Wait, we're talking here. My language does something different than C++, where first, so none of the destructors are throwing an exception in this example. I'm trying to sort out the semantic difference here between what you're doing in C++. None of the destructors are throwing an exception. Some base level low guy threw an exception, and now the tower of destructors are going to get called in some order, and the exception's getting thrown. And the thesis,
the last destructor first. So
yes, and they get thrown in nested order as you unwind them. Stack order.
Yeah, so that behavior is not different from C++.
Okay.
That's just
now we have another behavior, which is during the destructor, I threw an exception.
Yes.
Okay. And what is your language doing?
So my language, it says, okay, then we'll throw that exception, and we'll ignore the exception that
started. This is what Java does, and boy, it sucks. I'm not claiming either one of them is better, but I know I threw an exception inside an exception handler sucks.
So Alan, that means that you're also having to register a temporary exception handler during the unwind?
Right.
And while you're unwinding, you need to catch exceptions in the destructor.
Right.
And then throw the exception you have away or do something with it. I think Java nowadays throws it in a nested exception place and then has the new one coming along.
They've gotten better.
Well, yeah, you just don't throw the exception, right? You don't need to stash it away. Here, put it this way. Suppose I wrote code, I said throw exception A, throw exception B, right?
Yeah.
So
through A, you never evaluated B at all. You never evaluated the throw of B.
Right. And so it's the same thing when you're running well, let's see.
Now you've gone uphill one layer, you got a pending exception, you're running the destructor. The destructor says flush the file and close it. The flush call says I'm throwing disk full exception. but you already had an exception, a range check out of bounds exception. Now what do you do?
Well, now you throw the disk full exception because.
Okay, and what happened to the range check out of bounds exception? You just like threw it on the floor?
Well, it gets ignored the same way you ignore, like if you have a throw A and throw B,
Okay.
the throw B gets ignored.
So this is you don't tuck it away inside nested, you just throw it away and garbage collector will get it.
Yeah.
Okay, no, fair enough. And then as you run uphill, this sucks, by the way, but fine.
It's
Because people don't ever test their fucking destructor exception paths. And so it's always the case that you got some exception that shallowly died in an exception handler that was the destructor. And that only could have died because it came in with a funky ass bad state, but you lost where it came from and why you were there. So you don't have a clue why it was busted there.
well, I mean, if the disk is full and you throw a disk full exception, I think the right thing to do is to terminate the program. So you just don't catch the disk full exception.
I'm coming up with something that's sort of suitably plausible that left a whole lot of things in a broken state instead of just one. But instead I said I have a hash table which doesn't allow you to resize it and has a cap of 100 things and it got full. And so it's throwing a hash table full exception. Whatever. I throw a range check out of bounds in my destructor. I throw a range check out of bounds in that exception went uphill. I threw another one and I threw another one. And and I have some large complicated user-made structure that is now busted many layers deep, that the user doesn't understand how it is busted. And what do we do about it? He might know it's busted, he might not.
I mean, I think the thing is that, even though I'm allowing you to throw exceptions from destructors, like most of the time you don't throw exceptions from destructors unless like something has gone really bad.
Oh, right. So this is.
So assuming that the destructor exception is the worst one, is like it's not going to make anyone's life miserable. I mean, you says it's you say
I claim it sucks for debugging because I've been there a bunch, and you get log file hell, pukage.
We have to forbid exceptions for the greater good.
I'm in the zone of the destructor isn't allowed to throw an exception. But if you were wanting to have some sort of exceptional behavior and you're unwinding, then the destructor has some way to append more issues, but he's not throwing. But I don't know, maybe it's semantic, it doesn't make any difference.
Or list that can be populated as longer exceptions.
Well, the real issue is exceptions sort of can't be exceptions, really. They're just another state in the universe where you don't know what's going on. And what's the recovery point? And Cameron's thesis on XDC, which I totally am buying into here, is that there's some closed universe over here. It failed. Everyone has a narrow boundary to it where they got told this thing failed. They all have to have a decision process that works for their own personal cleanup, knowing that the other guy has failed. And they can't sort of blow it off and say, I'll just eat the exception and have another exception nest, right? So you're kind of, I think you're forced into better exception handling.
But we treat exceptions some kind of not part of the program, not part of the algorithm.
You talk to a hardware guy, and all states in the universe are states, and there are bad states and good states, but you don't have any exception states because there ain't no exception handling.
We've been through.
Not allowed to melt the hardware.
Exceptions. They're interrupts. Hardware.
No, but an interrupt is a very different thing than an exception or an error state. All errors.
You divide by 0 in the hardware. It throws the hardware interrupt. That's what you get.
That if you have an ECC error in your memory cycle, you do an interrupt. You have the x86 Q links between sockets throws a cosmic ray error. You have some sort of error state. The point is that you are required to declare it as just another state, like the one that says I'm reading bits off this wire and I'm looking at the ECC code and I'm all good and I'm about to come up with I took a cache miss and here's the cache contents I'm getting from this other socket, to I didn't get the cache bits because I got an ECC error because of cosmic ray. Okay, now instead of melting the chip and going up in flames or hard locking it and saying I had to power cycle to get it to come back, the hardware has that error as a state he's going to deal with, and he choices at the design point, I'm dealing with it here. I am dealing with it at a higher level, which will do a harder, larger decision. Like my Q-links cycling thing gets told, you need to reset yourself and what do they call it? Re-shmoo on the line to decide what the line frequencies and voltages are, and the line's stable, because that cosmic ray's got shit bouncing them down voltage-wise on that line until it stabilizes out, and you got to wait for that to happen for the line's actually valid again. So some higher point you stopped and said, I'm going to handle it here, and when I'm done handling it here, that error went away. But there were some lower level links that took some sort of error state, and they're passing it uphill. So kind of my thesis here is that this needs to happen whether you declare it nested or interlocked graph or something, but there are layers and layers and layers where here you have a reasonable point to handle it, and somewhere down below you can't handle it. You do not have enough information to handle it. So in H2O, we got disk full and we got out of memories because somebody loaded a giant ass data structure. Here's a terabyte, eat the terabyte on my laptop. Okay. So I ran until I hit out of memory. I caught out of memory. What do? Well, the out of memory handler has no fucking clue. Nor does the guy who says, I just opened this file and started reading bytes. I did a malloc of an array and reading bytes into it so I can screw around. He doesn't know either. The guy that can handle that is the one that says at the user mode's REPL, you said, eat this data structure. There it can be handled. And there the answer is, okay, guys, everyone stop allocating. Throw away all your megabyte giant arrays you just allocated for this data structure. Unwind back to it never got loaded state. I reclaimed all the memory on my laptop. And then back to the REPL, I'm good to go. And I hand you a nice error message saying, I can't load this, it's too big. But I couldn't handle it at the file load point. I couldn't handle it at the file parser point. I couldn't handle it at the malloc for the compression of the data. I couldn't handle any of those places. And there were dozens more that I couldn't handle it at, but I could handle it somewhere. And so the problem I see with the usual handlers story from Java, C++ and Java is, everyone catches in the middle where they can't handle it, and they have no good way to deal. They shouldn't bother to catch it because they're not doing anything useful. So somehow you have to preserve enough state to get to a point who can handle it without breaking everything in the middle to the point where it's not recoverable at all. And then the guy who can handle it has some way he's going to do a top level, I'm handling you now, and he cleans you up and lets you go. In the land of Java, garbage collection picked up the freed arrays. And I had to do a fork join cleanup, and the fork join has his internal state that said, I'm walking my FJQs, and everyone's who related to the following job get thrown out, and I eat them all up and throw them away. The FJQs cleaned out down to whatever was correct and proper for them to have, and things happen. I could do some cleanup, and I got it. So that was my long rant on what to do about exceptions. So Cameron's state is, I'm going to localize to this blob. The blob blew up. Everyone recognizes the blob blew up, but the blob's self-contained and it has its own heap. It has its own communication protocols to the outside world. We all got the communication protocol that said, this blob blew up. So we're going to cut the line to the blob. The blob might as well be a fucking separate OS process who also has the same problem, who then restores it all, cleans all the memory up and reclaims the resources. And then somebody says, make me a new file reader blob thing or whatever you're going to do.
But the problems always comes when this blob talks to other blobs, which in turn talks to other blobs.
The guy who failed has to have a border that says at any point where I fail, at that border where things are coming through, the guy on the other side can handle that failure. It doesn't propagate uphill and then I fail you and then it's too late kind of thing.
Yeah, but this is there is no indication in the program that it should or can. That's why
ask Cameron, he can do this.
If you propagate the exception with the type that this type can throw an error, then everybody is forced to know about it. It can.
No, they can say, I'm not catching, I'm not handling, and I'm getting broken. But I can run some destructor that says I'm getting out. If I can sensibly run the destructor at all, I can get out by freeing up resources. And then that exception carries on out. So I mean, I fucking doing some fintech thing, some dumbass guy made me exactly declare that I understood I throws an LDAP not found error. I don't fucking know what to do with an LDAP not found error.
These models frees you from the knowing all the exceptions that could happen.
Right.
You can.
I want to claim I don't know what the exceptions could happen.
If you know what exceptions can happen, they're not exceptions.
Yeah.
Okay, we're back to exceptions again.
I mean, it fundamentally boils. I don't mean to oversimplify it, but exceptions are super powerful. We ended up using them for everything except exceptions.
Yeah, that's the problem.
Okay.
They're basically semi-stateful go-tos.
Yeah.
So they're super handy, but generally a mistake. I mean, Dijkstra 1958.
Yeah. Go-tos. We all understand.
We could make the distinction that the exceptions are the universe of exceptions are pretty big. Some functions doesn't know some functions know some exceptions, but some they don't.
There's some unchecked exceptions.
An error is maybe in the category that error is an exception that is known. We throw an error, we know that we can throw an error, and we comply with it.
Java, unfortunately, called exceptions errors in a certain way in their hierarchy.
Yeah, you have this in spades in Java.
Errors were throwable.
Yeah.
And, they also confused everything with the checked exceptions issue, which is a non-composable concept.
Right.
So you ended up with,
that's why I
set the industry back a few decades.
Right.
I mean,
You
at the
catch
time,
all errors or throwables and rename them runtime exceptions, so you don't have to screw with it anymore.
I think it was Theodore, but it might have been Alan who was saying earlier about, so what happens when you divide by 0? That's an exception, right? And it's like, but it's actually a very reasonable question. Like, so someone divided by 0.
Yeah.
So what are you supposed to do now?
Yeah.
And my general answer, and don't take this as religion, like, because everything has to come down to kind of realistic, pragmatic stuff in the end. But, when there's an exception, someone must die. Right?
Yeah.
That's a good way to think of an exception, right? So you divide by 0, maybe the whole container disappears. Maybe it's just that service. Maybe it's at a request level, right? But something has to die. Some unit must die. Yeah.
Not somewhat.
What's the term?
Anthropomorphized.
Yes.
No, but it's a good answer. So here I am doing.
But don't take it religiously. I mean, obviously, there's exceptions to exceptions too.
I've kind of agreed that when exceptions happen, bad stuff is coming. That's for sure.
Well, right. There's a thesis that says I want to make exceptions difficult enough to write that you don't bother with the deciding incrementally who's going to die, except at some very high level where you have a chance of recovery after you kill off the dude underneath you.
Recovery, but not fixing.
Recovery.
Right. It's kind of like in Alcoholics Anonymous, not that I would know anything about it. There's a saying that, you don't recover from addiction. You're always going to be an addict. And it's the same thing for an exception. An exception happens. You don't ever become, you can't fix it. You just move on and, when we say recovery, what we really mean is kind of what's past is past, and we're going to move on from.
We're going to go around, different way going forward. Yeah.
Why not? Okay.
But in order to go forward, you had to have some recovery style thing that stopped and said, and now something happened here and I'm going to change the world and then try again doing whatever I'm going to do. So web server says, I took a divide by 0. Hey, bye. I took a divide by 0 on this web page. Fuck it. I'm just going to serve up the next web page.
Right. And you want some clean juncture where you can cut off whatever might have been corrupted.
Yes. Yes, that's a good point. There's an assumption that something got corrupted because you didn't complete. You built up some fancy state you didn't complete. It's corrupted. How far does the corruption go?
It could be 0 corruption. It could be infinite corruption. And the point is, you can't know.
The problem is when you build the code.
Corruption. There is no corruption. I really have to disagree here. No. Like at the hardware level, you're in an interrupt. it's instant. Like you just throw away the instruction cache and that's it. That's all you've done.
Well, there's your corruption right there. No, the hardware guys have the same corruption going on, but they declared all states and they just move you to a new state. The state of I'm in the middle of dealing with I can't subtract 0 from something and ever get an answer back out of it. So somewhere along the way, they changed to a new state, which was I'm now handling the divide by 0 error. And then that turns into, and I rerouted the program counter over to this point, and I had a huge out of order buffer that I stopped and I flushed out, and I had a bunch of pending stores that needed to be cached to memory. So I'll validate them, wait it out. So you stall there for a while he does the state, and then he says, okay, now I'll jump over here and begin handling, blah, blah, blah. Hey, but this is all part of the state handling. So I'm doing some sort of big data analysis thing. And one of my things is somebody wrote a stupid little, hey, give me the standard deviation of something because I'm just curious what the hell's going on. And they divide by 0 in the standard deviation because they screwed it up. At that point, it's a user written thing doing some small guy. I'm all ready to stop my entire program and go back in the debugger. But there's another one of those that says, during the course of running a standard k-means, I can have a cluster of size 0, it happens, and I want to recover the k-means algorithm. So I want to catch the divide by 0, go backwards from the nested recursive deep things that were doing k-means proportionally parallel distributed scale out, stop and catch it at some high level and say, this k-means algorithm can in fact carry on because I can catch the no cluster members and reinvent a cluster from the worst case dude or whatever the hell. There's a recovery mechanism that's obvious, and then you carry on with k-means. So you know, divide by 0 has the same property as file not found and disk full and God knows everything else. Whether you throw or you don't throw, there is a recovery point. It's at the OS level, at the command line, when your job vectored out all the way.
It's
the web server recovered.
That's all it is. It's a special return value from the operating system or from the disk or from whatever interface you're trying to use.
So now we're talking exceptions become I'm returning. I don't ever throw an exception. I'm not allowed to throw an exception. But I am allowed to return an error code. And maybe a tuple has an error code.
It's not a number integer, which is somehow not between -2 billion and +2 billion.
Yeah, right. Yeah. In the land of C programs,
unfortunately, we don't have such a concept. But
in the land of C programs, it's very commonly the case that people set aside some number to mean that the users decided this number means not a number.
And we included the exception in we made it an error, and we included it in the type.
Yeah, you know, in the OS guy, 0 was the only okay one, and all the things are errors.
We reserve a value for the exception.
For the common case in the integer world is, say, for instance, -1 or max int or min int. Like give me the index of this element in this array, or -1 if it's not in the array. That's you setting aside a -1 versus a positive value.
Yeah.
That's part of the API. And now you want to say, I can't throw. So a file operation like flush that says I have a disk full instead returns me an error code that says disk full, however that error code looks. And now I can deal from there. And everyone has to handle the errors as they go. And many people don't care to handle the errors. They want somebody else to handle it. And that gets you back to the exception state of, wouldn't it be convenient if I just had some shortcut that said, and if an error got returned, just return immediately with that error code and nested to do it. And I think Haskell, we don't have a Haskell light here. Somebody a couple weeks ago talked about this. Haskell does that as its normal default thing. There are no exceptions per se, but you can return a tuple with an error. And by default, if you return this, unless you put some other syntax in, everybody will test for this error and return it instead of carrying forward.
Well, that was my proposal, but actually that's not what Haskell does. Haskell has 3 methods of error handling, and they're all different, and they're all somewhat annoying.
Maybe one of them was what I just said. I don't know.
Like the Haskell, they have impure exceptions, which work the way that I described, kind of. Not really. They almost work that way. I'm trying to think. So, I mean, so the rethrowing stuff is what Swift and Rust have done. Like they basically said, you have this try keyword. And when you try a function that throws errors, then if it throws an error, then you return from the function with the error as well. So like it propagates the error. And otherwise you continue with the function. And
I'm
so
sorry, if I try a function, oh, okay, I see. If the function throws an error.
You write in a function foo try function bar, and then it'll if bar throws an error, then foo will return with the error. And if otherwise, you'll continue in whatever the code is.
And if you, okay, so the try basically says, that's what I was talking about. Yeah, there's special syntax that says at the point here, I think I can handle an error. So if you're going to throw one, I'll now inspect and handle it. And if I don't say try, it means I'm not going to handle any errors you throw. And you'll just immediately return at that program point with the same error carrying on.
Oh,
Yeah, but okay, here. You can go. You can
sorry,
go.
I just had a real quick question because you're gonna cut us off. Which was, when does Java fill in the stack trace? Like, is it
when does it fill in the stack trace?
It's not when I say new exception, or is it when I say throw exception? Because it doesn't mutate it. I'm just curious.
There's not a simple answer to this question, but generally you can assume that it fills it in right away.
Like when I say new?
New.
Okay.
Because once it's filled in, you can rethrow the same exception without crawling the stack.
Okay.
And if the throw and the catch are in the same compilation unit and you don't do a new, but you're rethrowing the same one, C2 will turn it into a computed goto.
And it's a fairly expensive, that's what makes exceptions in Java expensive.
The stack crawl is expensive.
Lock up the whole thing and make this data structure and then.
Yeah.
And generally in your typical modern application, you know, StackTrace is a megabyte of text. That
I wonder how much do people use that and versus not use it?
Use like that. What do you mean?
The stack trace, like if I catch it and at the top level and print it out to a log file, I used it.
Most people catch in the middle, print it to a log file and rethrow it, which then gets caught a few layers up, print it to a log file and rethrown again. And repeat 5 or 6 times.
The big challenge, Bill, is that you may not know where it gets thrown, whether or not it will ever get printed. So since you don't know,
you have to always fill it.
You either have to keep your thumb on the stack, which is impossible.
Right.
Or you have to fill in the stack trace at that point.
Yeah.
And so, and the other thing to remember is that in the Java case, the stack trace is a string.
Not anymore. I don't.
I did. They have a more modern thing with the stack frames and whatnot, but I mean, at some level, it's still.
I mean, I implemented all that shit, and you build up a complicated thing that's expensive to build because of how they specialize or spec it, but it's not a string. There's an array of members that are unrelated to things that can be turned into a string. There is a stringified hash. There's probably a cache of a string version if you actually stringify it. There was a hidden internal guy that was intended to be cheaper that showed up late in life. But maybe that's directly what I was doing though. So when I crawl the stack,
StackTrace element is the inner class.
Yes.
Use.
Yeah. When I crawl the stack, I believe I gather enough information from the crawl and throw it in a side buffer that you don't get to see. And then StackTrace elements as a reflective Java object are wrapped around them. And then later somebody will crawl StackTrace elements to build you a string if you ask for the string to print. And the sadness is that, you know, those crawls could be actually made pretty damn cheap. They're never free because you have to actually crawl. At Azul, when I was doing like a random stack sampling, I got most stack crawls down to, I want to say mid nanoseconds per element on stack. Like you crawled for a computed frame. I needed a computed frame, I needed a program counter, which gave me stack frame and that stack of inlines that went with that because it was a compiled frame, and it got me the next guy. So I do a program counter into a hash table, which returned me a pointer to a struct, which contains the size of that compiled frame and one other bit that I needed to know. And then I added the size and repeat, lather, rinse, repeat. Did an out of bounds check, lather, rinse, repeat. So the hash lookup was however long a hash lookup was, but it wasn't very slow. You often got a cache miss, so I have to increase my estimate here, getting at the metadata if exceptions were rare. If you're throwing it a lot, then you're going to cache hits. But if their metadata was rarely looked up, yeah, you'd play a cache miss per JITted stack frame. Once you got into the interpreter, there's not going to be any misses, and you had more frames, but they were all small looking things. And then, as Cameron says, a big application, maybe you have 100 of these things to crawl. You probably have dozens compiled ones and half hundreds to crawl in the interpreter. Top layers probably all got JITted eventually too.
Yeah, I was just thinking the thing I would advise people was only use exceptions when you throw them at people, like at a developer or an ops person.
Yeah.
What that is it's they want to see the stack trace for forensics to figure out what went wrong, and then they fix it. A human fixes it. So really, it'd be another way to think of it is only throw an exception if you want that.
The usual story is that your exception gets written to a log file.
Yeah.
A billion times a second by a billion people, and no one ever looks at it.
Yeah.
Yeah, so like my solution is that exceptions don't have stack traces. They're just values, and you pass the value, and that's it. That's all you get. If you want to look at the stack trace, you use a debugger.
Okay, let's see. How's your debugger do it? And the answer is you have a special hook for the debugger, but you're not allowed to call that hook. Like if I wanted a stack trace, I have some horrific path where I'd call into the debugger and have him give me the stack trace and bring it back. You're going to have a stack trace.
Yeah, I mean, just to go back a few years to when we didn't have stack traces, Alan, please take my advice and change your mind on this one. Because holy fuck, C++ was a pain in the ass for debugging exceptions. And I can't even begin. I've almost surgically removed that part of my mind. It was so painful.
Well, I certainly did all hotspot development in C++ without any exceptions.
But tell me I'm wrong, Cliff. Like,
oh no,
like there were no stack traces. You had no idea where something like.
And you loaded up the binary and you prayed to God that you could get an equivalent build, and you frequently got an equivalent build which had debug info. And then you could.
The process terminated with -1.
Yeah,
that's exactly what I needed to know.
Exactly. Yeah, and if you got that, then you got nothing. Yeah. That's the JVM terminate. So no, all you could do there was rerun the thing inside the debugger and pray to God it would crash again on the debugger.
In the same way, exactly.
Yeah. And you would frequently not. Big, hard, heavy loaded Java system, all JITs flying, all garbage collections flying, dozens of threads running on a big server going off, all kinds of concurrency shit happening. Something broke.
Alan, my advice to you is no matter how painful and difficult it is to do a stack trace for an exception, do a stack trace for an exception.
Oh, while I was at Azul debugging some stupid thing, I got a new dump from Sun that claimed to fix it. So I took it. That turned into, upon they had added new stuff, which was do every possible information gather you could do in C++ upon getting some issue. And in the port, as it came to me, it meant that where I had my original crash now went to the debug handler to go gather some information. That crashed. That went to the next layer up debug handler to gather information, which crashed. I am not kidding. This went more than 15 times deep. So I started at the innermost one of those, or the shallowest, whichever you want to go, and began unwinding over the next 2 weeks where their stack trace information gathering was broken when it was dealt a broken hand. If the world was all valid and correct, and I stopped and said, call the debug handler, he gave you a nice, pretty answer with, here's all the Java heaps, and here's all the objects nearby, and here's the stack crawl, and here's the this and that. It all came out perfect. Anything was fucked up, he was dead. And if you go look at my prints in AA for like, go print this large complicated data structure, all of the string printers are all smart about handling broken structures.
Yep. So Simon had some questions and he had to go, so we wanted to make sure we captured those.
I see Simon right there. You mean Bill? No, Bill's right there.
No, Simon has to go, he said.
Oh.
Simon, what did you want to raise?
Let's do it another time. I think it's like in the last
We're like
minutes.
2 hours in plus change.
Not,
Well, I was
it's
thinking
not
we
a
could take
smart
notes
idea.
on it so we
Give
could
us a hint.
remember.
Yeah, give us a hint. Like trailer.
So yeah, I had some progress reports one thing was that I asked a while ago regarding the modifiers versus annotation topic, and I had some things to report, and also on some enum business and on some unified condition experiment that appears to be working out quite nicely. So yeah, let's see.
Well, you can wait till next time, but I'd be interested to hear. All right.
So there's a solution though, which is that you use the reproducible debugging stuff. So like then, so then you don't need a StackTrace because you have omniscient debugging.
Yeah. Go back 20 years and tell me that. I'd knife you. Use my little friend. 2 weeks in a debugger trying to diagnose shit in the same core. No.
Yeah, but that's why the exceptions don't have StackTraces, is because the debugger is much more powerful. And so you always run the program with tracing so that you can reproduce the exception.
Yeah, okay. So the first thing that happens is when it runs in production, no production guy is going to give you root permission or a debugger with root permission. So
well, you can debug the trace, so you can debug the trace locally. So.
You claim that your Bank of America guy running your job in his production environment that just blew up is coming to you on a support call, and he's going to hand you the core file that contains the names and ranks of every of his customers and all their account balances. The answer I'll tell you right now, sir, is having been there, no. It wasn't B of A, it was Deutsche Bank. And the answer was no. Root caused this, or we'll cancel your 10 million a year annual service contract and no core file.
Huh. Well, say like, I mean, this is exactly why you don't want StackTraces, because debugging is so much better, and it'll force these Bank of America.
I'm just saying, you know, there's a difference between maybe debugging a thing that is implementing your garbage collector from debugging the thing that is running with the garbage collector. You know, this is the OS guy. I'm debugging my OS's context switch without having an OS to context switch, because that's what I'm debugging. Right. I mean, you at some point you lose out on all these fundamental capabilities, and you still have to do something to make forward progress. And I don't know what the right answer is. Sometimes, you know, you're totally correct that debugger is way more powerful. There are certain environments where no one will ever let you attach a debugger as a par for the course. About, you know, how the debugger.
We actually have a plan. Interesting take on this too, which is, you know, so we run each app in its own container, and the containers are services hierarchically arranged within our runtime. So for us, a debugger is just a container, a specialized container. So
and how do you debug the debugger? How do you debug the debugger?
I hear the question, but I'm going to defer that. I'm going to defer that talk.
Because I've been there.
I actually like the question, but I'm not ready to answer that.
Okay, fine.
It's actually a very valid question, because theoretically, if the debugger is kind of built as a ecstasy service, you should be able to debug the debugger. Yeah.
Right, and the answer is that you have something broken in your debugger because you're fixing it because you're working it for the first time, and every time you use the debugger to attach the debugger image, the debugger you're using to attach to crashes. I was writing a kernel debugger, and I had to debug the kernel debugger. So I was debugging the kernel debugger with the kernel debugger, and I knew that if I did this thing that should work, I will crash because the nested meta layer was going to blow up on me. So I was trying to gather information in peek and prod memory without actually using the debugger to peek and prod memory, because if I did that, I was going to blow up and die. And, you know, it's like a Viking.
That's why we used to have ICE debuggers.
Yeah, exactly.
What did that stand for?
In circuit emulator.
Circuit emulator. Yeah.
Yes. I eventually got my kernel debugger debugged, and then I could use it to debug my kernel, and then I was, you know, up and running reasonably. And
because in Windows I use soft ice.
Yeah, these days you might be able to. Virtual machines are well enough along that you could do that now. The virtual machine.
Yep.
Yeah, back in the day, no such virtual machine support. You did it, bootstrapped it every time. Fine.
Well, see, this is why you
should be able
need
to
proper exception handling. If you have proper exception handling, then your debugger will handle the exception instead of crashing.
Maybe. You know, I run IntelliJ, right? It's using Java. I have 2 string calls of complex cyclic structures. It is commonly the case that a 2 string call stack overflows. So in the debugger, when it pops up the variable printout window, it says ... collecting information. And it used to like not collect any more information because it was hung trying to collect the 2 string on the 1 dude. These days, they fix that bug, and all the dudes that take too long, they cut off and say, I'll give you the raw object view, but not the 2 string print, which was so much nicer. They still have the bug, though, that I'm debugging a Stack Overflow exception, so none of the 2 strings, shallow or deep, can be run. But I can throw frames away. But I really want to know is, where did you start the infinite cycle that led to a recursion, for which I have to throw away 10,000 frames? And I can't scroll to the bottom because every time I do, it does an n squared version of gathering all the frames before. So it'll whip down the first tail half of the 100 frames, and then it'll incrementally slower and slower and slower get more and more frames. So I grab the slider and I slide it up, and it suddenly says, and the n squared shrinkage is like, I can do my timer on my phone, and you know, maybe 15, 20 minutes, I can get to the bottom and see the guy. That's the root. And I know he can instantly crawl to the bottom, give me that, but he won't. He stops and gathers. So if I pop a few hundred guys, probably dozens of guys, I get the normal 2 strings that aren't being deep and recursive, and I can probably diagnose that the recursion itself is only 5 frames.
Exponential big O is actually a problem even on a fast processor.
Yes. Yeah. Yeah, exponential grows really fast. I'm hoping almost only n squared in this example, maybe n cubed, but that's already ugly enough. But exponential.
Big O equals big headache.
Yeah, yeah. That's my caveman counting. 0, 1, many. Ugh.
Yes.
All right.
All right. Done.
Yeah.
Lunchtime.
Yep.
It was fun. Till we meet again.
Okay, bye.
Bye-bye.